Okay, so this lesson is being recorded on Zoom just to save us some time in class for going over some of these special cases. So you can follow along. There's a handout that will go along with this. You'll see it show up in a little bit, but I want to go over the PowerPoint first in terms of the basic information here. So this is called matched pairs inference. If you remember back to experimental design earlier in the year, there was something called matched pairs when we wanted to compare two different treatments in a certain scenario where there's lots of variables involved. Matched pairs was one of the type of solutions. So we want to look at see how the inference procedures go along with this type of a situation. Okay. So there are two main forms of matched pairs. We can pair individuals by certain characteristics. So randomly select treatment 1 for individual A, individual B is assigned the other treatment, and then assignment of B is dependent on what's assignment to A. Okay, and then you compare results later. Sometimes we switch the results and compare them both ways. Other times we can compare one individual person that receives both treatments, okay, or item that receives both treatments, okay. So we randomly assign a before and after, and then take measurements at the end. Sometimes we saw the example with the shoes. You know, we had a right shoe and a left shoe, and then you switch things. So lots of examples of matched pairs. These two measurements are dependent on the individual, okay. So those are a couple examples of matched pairs. Usually with experiments to compare, we broke subjects into two different groups. These are situations where that doesn't work very well because there's lots of variables we know about. So we pair either two people that are close together as possible, or give one person both treatments just in different orders. Okay. So we're going to look at some examples and be able to pick out if they are matched pairs. So the college wants to see if there is a difference in time it took last year's class to find the job after graduation, and the time it took for the class from 5 years ago to find work after graduation. Researchers take a random sample from both classes and measure the number of days between graduation and the first day of employment. So is this a situation that would be considered matched pairs? Okay, the answer is no. Okay, there's really no pairing going on here with individuals. The two samples are independent of each other. Okay, so not a matched pair situation. Here's another one. In a taste test, a researcher asked people in a random sample to taste a certain brand of spring water and rate it. Another random sample of people is asked to taste a different brand of water and rate it. The researcher wants to compare these samples. Okay, as with the last one, no, we're not pairing any individuals. We have two independent samples that don't overlap. If you would have the same people taste both brands of the random, then it would have been an example of matched pairs. But since we have two separate groups, this is not matched pairs. Okay, one more, and you can guess that this is going to be a yes. A pharmaceutical company wants to test its new weight loss drug before giving the drug to a random sample. Company researchers take a weight measurement of each person. After a month using the drug, each person's weight is measured again. Okay. Yes, we have two measures that are dependent on each other. So it's a dependent relationship, and we often have one group being tested, not two different groups. Okay. So here's an example we'll work through together, and I'll justify why it's a matched pairs again. Sorry, this box for the Zoom session is in the way. So a whale watching company noticed that many customers want to know whether it was better to book an excursion in the morning or in the afternoon. To test the question, the company collects the following data on 15 randomly selected days over the past month. Note that the days are not consecutive. Okay, so we've got, let me move this thing again. Sorry, I'm going to have to keep doing this. We've got the different days, and we've got the amount of whales seen in the morning for each day and the amount of whales in the afternoon seen. Okay. Go back. Okay. So So since you have two values of each day, they are dependent on the day, which makes this a matched pair situation. First, you must find the difference for each. Okay, so what we're going to have to do is to do the math on this, we're going to have to subtract each one of these, and you want to pay attention to the order. So we want to do morning minus afternoon, and use that for our inference procedures later on. Okay, so you can subtract either way, but just be careful to note what that is, because that's going to impact our alternative hypothesis. Okay, before we start writing our hypotheses, our null and alternative, we want to think about how we can do that subtraction. And this is a way to do it on your calculator. This works for both confidence intervals and hypothesis tests. So what I would do, and you'll see me work through an example later, is type your first set of data in L1, your second set of data in L2, in this particular case, mornings in L1, afternoons in L2, and then go over to list 3 and up at the top, highlight your equation bar, and then just simply do L1 minus L2, and that will give you the differences for each individual day. Okay. Then after that, we know when we're doing inference of quantitative data, we always want to look at the graph when we have small sample sizes like this. In this case, we have a sample size smaller than 30, and make sure there's no outliers or skew before we run our test. So you could, after you've typed in your data and found the differences in L3, then just run a graph for L3, either a dot plot, or there's no dot plot, a histogram or a box plot. The safest one is probably a box plot with the ones that show outliers, because what we are looking for is either outliers or strong skew in either direction. If you have any of those, then you can't run the test. If none of those are present, then the test is good to go, or the confidence interval is okay to run. Okay, you can see here there's also something called a normal probability plot. We really haven't gone over those. They're not going to really impact what we need to this year. Okay, so that's how we would get through these. You see, I made a graph for you. I calculated the differences. I typed them in here, and then I made the graph and made it as a dot plot just so it was visually easy to see. So if I subtract morning minus afternoon, you'll see a lot of the values come out to be negative. Make sure the assumptions are in terms of the differences, not the other parts and the conditions. So the assumptions and conditions, we have independence because we are given a simple random sample of days. They're not consecutive days, they're randomly selected. And we have to assume that this is less than 10% of all the days that they will be watching whales. So we have to assume that they've been doing this. 15 times 10 is 150. So we have to assume they do this over more than 150 days to make their decision. Okay. Normality, again, we have a sample size smaller than 30. So we just have to check, since we don't meet the central limit theorem, we check the graph and make sure there's no strong outliers or skew. Okay. So we can see here, there's no obvious skew. So it's reasonable to assume that the sampling distribution in this case would be approximately normal. Okay. So is there sufficient evidence based on these differences that there is more whales sighted in the afternoon? Remember to be careful how you subtract it. So morning minus afternoon. We look at the differences, and more would be a negative number, right? Because the second number would be the bigger number. So morning minus afternoon, if we think the afternoons or more sightings, it would be a smaller number minus a bigger number. So it would be a positive. Okay. We assume because of how these tests work that there really is no difference between morning and afternoon to begin with. And then we have to find statistically significant evidence that it's different. Okay. Sometimes if you're not sure which one would be better, you just have to do a not equal to case. But because of the way that the question was worded here, is there sufficient evidence that there are more whales are sighted in the afternoon? Then you have to follow along and answer the question being asked. Okay, so your null and alternative, your null, the mean difference is nothing, that they are actually the same. The alternative is that the mean difference is greater than less than 0. So it's a negative since we're doing a smaller number minus a bigger number. Okay, and then they use mu of d and define what that is. So that where the mu of d is the true mean difference in whale sighting from morning minus afternoon. Okay, notice that they say mean difference here and not the difference in means. Be careful with that wording. It'll become important later on when we look at comparing two separate populations. So in that case, later on, we'll say difference of means. Here, since we're just looking at one number, you're just looking at the mean differences. So try not to get confused with that. Okay, so since this is a hypothesis test and it's for means, we would do a t as our test statistic. So sample mean minus the assumed population mean divided by the square root of sample over the square root of n. You plug all the numbers in that you got from the inference procedure. So obviously you would have to calculate your summary statistics for this list of data at the top. This would be the mean, this would be the standard deviation. We assume that there's no difference, so that's where the 0 comes in here, and our sample size is 15. Okay, and again, you could run all this on your calculator doing the t-test, okay? And that'll give you all these numbers that you need. And then we've got our p-value, which is 0.1803. Again, your calculator would give you that. Degrees of freedom, 1 less than the sample size. And at a significance level of 0.05, when you compare these two things, we're gonna see since this number p-value is much bigger, we would fail to reject the null, okay? So there is insufficient evidence to suggest that there are more whales sighted in the afternoon than the morning, okay? So we don't have any statistical evidence of any difference between the two time periods, okay? And remember, if you want to do that work on the calculator, for the problem we just did, it would be a t-test. You hit stats, then go over to test, and in that case, it would be option 2. If you were doing a confidence interval for the mean difference, just trying to estimate what that would be for a matched pair situation, instead of assuming that it's 0 and trying to prove differently, if you just wanted to estimate that using a confidence interval, instead of t-test, you would do a t-interval, okay? So that's it for the PowerPoint. Now let's take a look at some of the problems on the worksheet that you have to record things on. So I'll switch it over to the document camera. My audio might get a little bit lower because I'm further away from the mic, but I will do my best to remain loud, okay? So the first side here talks about the confidence intervals for paired data. I described some important ideas up at the top. We'll look at confidence intervals first and then hypothesis test second. Okay, so an important idea is our assumed difference is often 0. If the second number is larger, then you're going to get a negative for the differences. So smaller number minus a bigger number is a negative number. If the first number is bigger, that would be bigger number minus a smaller number. That means that your difference would be a positive number, okay? And remember, we're trying to estimate not just the mean in this case, we're estimating the mean difference, okay? We would still use the one sample t interval since we're only dealing with one list of data, and that would be for not just, instead of in the previous problem we did one sample t interval for means, now we're looking at, just to add one more word, one sample t interval for mean differences. Okay, so when you're doing matched pairs, you just add that word differences at the end. The calculator function you'll use is still t interval like the one sample problems. So you'll calculate it the same, it's just a little bit different type of a problem. Okay, and this is what the formula would look like, or the expression would look like. Just instead of x bar, it's the x bar of the differences and the standard deviation of the differences. Okay, so here's a sample problem. If you have your calculator available, you can pause this video at times to kind of look at things as we do. So researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from colas, and other substances with caffeine for a duration of the experiment. During a 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took the caffeine and the placebo were randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression at a significance level of 0.05. And we will answer questions about that in a second. It says the table below contains data on the subject scores on depression test. Higher scores show more symptoms of depression. So higher is more depressed. Okay. So you can look at your data here: depression based on the caffeine, depression based on the placebo groups. Okay. So the first thing we want to do to kind of look at the distribution here is make a dot plot of the differences in depression or test scores, caffeine minus placebo for each subject. What does the graph reveal about the differences in depression scores? Okay, so in order to find that quickly without doing every subtraction by hand the long way, what I suggest doing, because you'll use this stuff later anyway, go into your calculator, and what you're going to do is go into the stats menu and enter the data in your list. So hit stats, and then under edit, just hit enter. What you'll do is under L1, you're going to type the caffeine data, the caffeine scores in that list. Then in L2, type the placebo scores in that list. Okay, and you can pause the video while doing that, and come back when you're done. Once that's ready, what you want to do is go over to L3 to save yourself some time. Go up to the actual list name, L3, and have that highlighted with the black bordering there. And once you have that highlighted, you're going to do L1 minus L2 as a formula, and that'll automatically calculate all the differences for you. Okay, and just as a reminder from earlier in the year, your list names are above each of the digits down below. So I can hit second L1 minus second 2 to give me L2, and you can just see that on the screen to verify that, and then hit enter, and what that'll do is calculate all the differences for you. Okay. Now, unfortunately, the calculator doesn't do a dot plot for you, so you do have to do that part by hand in here. But if you are running an inference test on an AP exam, you could easily go in and do a box plot of this data over here by hitting second and then y equals. That'll get you your stat plot menu, and you would turn that on, select your box plot with the outliers. I think that's the safest one because we're looking for either skew or outliers. And if those aren't present, then we're good to go. And then you would hit zoom and then go down to zoom stat. Okay, and you would see your box plot there. Okay, so that's perfectly fine to do. In this particular case, they asked you to do a dot plot on the paper, so you would just look at your list and draw a rough sketch of that. You see the numbers were between -20 and a little bit less than 5. So I just drew a rough sketch of that there based on just eyeballing it and setting up a scale. Okay. What does this tell us? It says most of the dots are negative. This means that the placebo scores were higher. Okay. And as you can see here, the dot plot is a little bit, the box plot is a little bit misleading sometimes in terms of shape. Especially with small data sets like this. So the box plot almost looks pretty skewed there, but when you look at the actual dot plot here, it doesn't look that bad at all. Especially with a small sample size, it's hard to tell, but there's nothing saying it's a really strong skew. It looks pretty spread out and nothing bad there. So nothing wrong with that to run the test based on that view. Okay. Then we can take a look at part 2 here, find the mean and standard deviation of the differences in depression test scores, interpret the mean differences. In this case, you could do it a couple different ways. You could do one var stat of list 3, you know what? This is wonderful theater here. I know why that looks weird. I did a list 1, and this is something that you guys can check too. I needed to do list 3. So second list 3, that will make more sense. So list 3, zoom, stat. Okay, that's a much better picture. So that's what the graph actually should have looked like, not the original one. Sorry about that. But you could do 1-bar stats in order to find the mean differences and the mean standard deviation. That's perfectly fine. Or since eventually you'll have to do the t interval anyway, that information will be in there as well. So I'm going to do that to save myself some time. So stat, then over to test, and then I'm going to go down to t interval. That's option number 8. I'm going to use the data this time, but not make the same mistake I made earlier. I'm using the data from list 3, so I'm going to do second list 3. My confidence level is 90, so I'm going to go down and calculate that. And you can see they give me my interval, they give me my mean difference there, so negative 7.364. My standard deviation of the difference, 6.918, okay? So what this means is on average, the placebo was about 7.364 higher than the caffeine. Okay, so this is statistical evidence that the placebo group did have a bigger impact on the stress, meaning that the caffeine reduces the amount of stress for these caffeine-dependent people. Okay, and you can see the interval here. That's what we have down at the bottom. This would be the work for showing your work. So it says construct and interpret a 90% confidence interval for the true mean difference in depression scores, caffeine minus placebo. So this would be your formula. So the mean difference from the sample plus or minus the significant critical value t, so critical t divided by times the standard deviation of the differences divided by the square root of the sample size. Okay, so these numbers you have already from the given or what we just calculated. Our sample size is 11, so our degrees of freedom would be 10. You can find this, if you have to do this by hand and show your work, you can find this critical value, again, by going, the quickest way is probably by going to your T table on your formula sheet. That would be table B. Remember, these tables will be at the end of the AP exam. So we look for our degrees of freedom, which we just said was 10. And our confidence level, we can find that at the bottom, which is 90%. And we kind of work our way together with those two directions. So to the left of 10 and up from 90. And we get this 1.812. And that's where they got that number from. Okay, so if you have to show your work by hand, the only thing that you need to figure out is that critical T. If you're doing this on a multiple choice, you don't have to worry about that. Okay, so then you interpret what this interval means. It says we are 90% confident that the true mean difference, caffeine minus placebo, and depression scores is between negative 11.14 and negative 3.58. So that would be evidence that the giving caffeine-dependent people caffeine pills when they are deprived increases their depression compared to a placebo. Okay, so that's an example of a confidence interval. On the back here, we have an example of a hypothesis test. A lot of similar stuff. You would use the t-test, but then when you're describing it, you would just say it's a one sample t-test for the mean differences. Okay, and all this other stuff is the same, except for instead of just mean and standard deviation, it would be the mean of the difference, the standard deviation of the difference. Some textbooks, as you saw in the PowerPoint, just let you put a D there. A lot of times it's a capital D. Some textbooks put it like this with a D-I-F-F. Okay, and I wrote over here, again, another way to test to see if it's a different match pairs or two population situation. If there's only one sample, that's match pairs. And what we do is we subtract the averages and then we have only one mean. Okay, two samples, we've got two groups, two averages, and then we average, then subtract. Okay, so that's another thing. We already kind of went through that, but that's just another thing to look for to compare the two. Okay, so here's an example of a hypothesis test for this kind of thing. It says, suppose that 32 seniors were randomly selected to try both memory strategies. Each student calculated, strategy 1 and strategy 2. Each student calculated a difference in the number of words, strategy 1 minus strategy 2. The mean of the differences was X bar of differences, 1.5, and the standard deviation from the sample was 2.7. Do these data give convincing evidence that strategy 2 improves the memory at a significance level of 0.05? Okay. So with any of these, you do your state plan to conclude. With a hypothesis test, it's a little bit more structured and organized. So our parameter is the mean difference. We're looking for the true mean difference in words. Our null hypothesis would have to be that there is no difference between the two strategies. And based on the question, the way that they asked it, strategy 2 improving, that would be, if it is true, it would be a bigger number minus a smaller number. Bigger minus smaller is a positive. So that would mean the mean difference is a greater than 0, so a positive number. Okay. And your statistic you're working off of, the mean difference is 1.5. Your significance level is 5%. So just like before, we have to name these things. It's a one sample t-test. That's what we've been dealing with lately. But now, since it's a matched pairs, it's a one sample t-test for the mean differences. Our conditions are pretty much the same. We have a random sample of 32 students and seniors in this case. Now, in this case, since we are testing against ourselves, it's fairly reasonable to say that one student will not impact another. So there's true independence here, and we don't have to worry about drawing without replacement since we're not impacting other students at all. So we have true independence here, so we don't have to test the 10% condition. Okay, this is essentially an experiment, but it's also a rare case where we're randomly selecting it. So not only can we draw a conclusion at the end of the cause and effect, but we can also apply it to a larger population, which is kind of cool. Okay, that's very rare, but we were able to do that in this case. So, and then the other thing is normality that we test for. Since our sample size is bigger than 30, we have a large enough sample size to meet the central limit theorem, since it was 32. Okay, so that gives us, the central limit theorem gives us confidence that the sample distribution is going to be approximately normal. Excuse me. Then we do the math. Again, we're assuming that the mean difference is 0. Our standard deviation, we could calculate that. Standard deviation of the sample divided by the square root of the sample size. You don't have to put this general formula on the AP exam. You can just put this in there and plug in the appropriate numbers. A nice little rough picture, assuming that the center is 0, that there is no difference. The probability of having a difference of 1.5 or greater will be represented by this picture. That's perfectly fine. You could, I guess I forgot to write on there. This is a t-distribution, and the degrees of freedom are 31. All right, almost done here. So then you plug in the appropriate numbers. We assume that the parameter is 0, that there's no difference. What we observed in our sample was 1.5. Our standard error down here was 0.477, which we calculated up a little higher here. So the probability of observing something this many standard deviations away or more extreme is our p-value. So thinking about this, this represents a little bit more than 3 standard deviations above average. So my picture is probably a little bit inaccurate here. I would have even less shaded visibly, probably on an accurate picture. So whenever we're more than 3 standard deviations above average, that's pretty much considered an outlier in any situation. And that's verified by this p-value being so small. Okay, so since our p-value is 0.001, we're going to have enough evidence to reject the null. Okay, but this math will support us there. Okay, so once we have that down, we can make our conclusion. So assuming that there is no difference between the two strategies, strategy 1 minus and strategy 2 minus strategy 1, there is a 0.001 probability of observing a sample mean difference of 1.5 or more purely by chance. This is convincing evidence to reject the null. We can conclude that the difference is greater than 0, and this is supporting strategy 2 as a more beneficial memory strategy. Okay, so that's a couple examples of this. One, actually two hypothesis tests, if you include the one from the PowerPoint, and one confidence interval. Okay, hopefully this will give you a couple examples to be confident with this topic and the math behind it. And as always, thank you so much for watching.